Hello, everyone. My name is Abhishek, and today I'll be talking about computing homological hitting sets. This talk is based on joint work with Ulrich, Bauer, and Meirav Zehavi. So as we all know, graph cuts are have a ubiquitous presence in theoretical computer science. Graph cuts have found applications in clustering, shape matching, event segmentation, energy minimization, and so on. Graph cuts also come in various guises like min-cut, min-ST cut, min-multiway cut, sparses cut, and so on. Our goal in this book is to generalize the notion of cuts to simplicial complexes. To keep the talk accessible to a wider computer science audience, I'll briefly recall some of the elementary notions in algebraic topology. So here's my brief review of simplicial homology. So suppose you're given a simplicial complex K, then we denote the P simplices of K by Kp. Next, we define a P chain as a formal sum of P simplices of K. And for the purpose of this talk, we'll be working with Z2 coefficients. So effectively, we can view P chains as a subset of Kp, where Kp is the set of P simplices of K. The P chains of the complex K under Z2 addition form a vector space called the Pth chain group of K, and we denote it by C subscript Pk. Next, we define the boundary map. So to begin with, for a P simplex sigma, its boundary partial P sigma is given by simply its set of P minus 1 faces. Now the boundary map is then linearly extended from P simplices to P chains, and this gives a vector space homomorphism from the P chain group to the P minus 1 chain group. So continuing from the previous slide, we've already defined what partial P is, or boundary P is. So the kernel of this map partial P is called the Pth cycle group of K, and it's denoted by C subscript Pk. And the elements of this kernel are called the P cycles of complex K. The image of the map partial P plus 1 is called the P boundary group of complex K, and it's denoted by B subscript Pk. The elements of the boundary group are called P boundaries. The Pth homology group of K is obtained by taking the quotient of Zpk by Bpk. Moreover, two cycles are said to be homologous if their Z2 difference is a boundary. And the set of cycles homologous to a given cycle zeta is known as the homology class of zeta, and it's denoted by square bracket zeta. Finally, a cycle that is also a boundary is called a bounding or a trivial cycle, and a cycle that is not a boundary is called a non-bounding or a non-trivial cycle. Okay. Now that the review is over, let's do a simple example to build some intuition. So in this example, you see a planar complex with a hole in the middle. The inner cycle zeta 1, the inner cycle zeta 2 is depicted in purple, and the outer cycle zeta 1 is depicted in blue. And as you can see, zeta 2 minus zeta 1 is a boundary, and in particular is the boundary of the triangles that are shown in pink. So for this example, zeta 1 and zeta 2 are actually homologous. So this completes my description of this example. And next we will recall some notions related to surfaces, and because surfaces constitute an important class of simplicial complexes. And also we have some results for surfaces. So many of you must have encountered surfaces such as the cylinder, the Mobius strip, sphere, torus, Klein bottle, real projective plane, and so on. And of these surfaces, the surfaces with boundary are the cylinder and the Mobius strip, and the surfaces without boundary are the sphere, the torus, the Klein bottle, and the real projective plane. And next we'll look at the definition of simplicial surfaces, which are basically triangulations of surfaces. But to begin with, we define the star of a vertex of a complex. So the star of a vertex, V, is the subcomplex of consisting of all simplices containing vertex V along with their faces. And a triangulated surface is a simplicial complex in which the star of every vertex V is a simplicial disk. So basically, locally, it looks like a plane. And a closed surface is a surface that is compact and without boundary. So in context of this work, the surfaces that are interesting are closed surfaces that are triangulated. All right. Now that the preliminaries are over, let me go to what was promised in the first few slides, that we're going to generalize min cut or min cut. So let's try to do that now. So recall that min cut asks for the minimum number of edges whose removal disconnects S from T. And equivalently, we can say that is the minimum number of edges that need to be removed so that there is no path connecting S and T. However, there is a path connecting a vertex. There's a path connecting vertex S to vertex T if and only if the boundary of the path is S plus T. So the homological formulation of the min cut problem, min cut problem, is what is the minimum number of edges you need to remove so that S plus T is not a Z2 boundary. Now, the image generalization of min cut simplicial complex is a problem that we call boundary non-trivialization. So let's try to understand what this means through an example. So in the example shown here on the slide, we have a complex L, which consists of triangulation of a union of two spheres that intersect in a circle. The circle of intersection is denoted by B, which you probably cannot see because the font is too small. And the question is, well, what is the minimum number of two simplices you need to remove so that B is not a bounding cycle anymore? So why is it a bounding cycle? Because you have two caps on the top and two caps on the bottom. And for each of these caps, B is a bounding cycle. So you need to remove simplices so that B is not a bounding cycle anymore. So the minimum number of triangles that are two simplices that you need to remove is, of course, 4. You need to remove 1 two simplex from each of the caps, and then B is not a bounding cycle anymore. Now, this example completes my description of this problem. I will not say more about this problem because we don't study this problem in this paper actually, but I only described it because it's a direct generalization of min cut. But actually, we explore this problem in more detail in the extended version of our paper, which is on arXiv. Instead, we look at the dual version of this problem, which is called the homological hitting set. And for the remainder of the talk, this is what we'll talk about, dual problem, which is homological hitting set. All right. So what's homological hitting set? Before I formalize with the definition, let's once again look at an example. So in the example shown in the slide, you have a planar complex K, and two cycles are depicted, zeta and xi. And the cycle zeta is depicted in green, but there's another cycle that's homologous to zeta that's also depicted in green. Now, so the question is, well, what is the minimum number of simplices you need to remove so that the class of zeta is destroyed? Equivalently, what is the minimum number of simplices, or what is find a set of minimum cardinality, set of edges of minimum cardinality, such that every cycle in the class of zeta meets an edge from this set. So if you look at, in this example, if you look at the set of edges shown in red, if you remove these edges, then the class of zeta is destroyed. So, okay, so that's what is the homological hitting set problem. This is a cut problem in the sense that finding a minimum cut, or in this case, a minimum hitting set, is equivalent to removing simplices from the thin portion of the complex. Now let's try to make a formal definition of the parameterized version of the problem. So you're given a complex K and an integer little k, and this integer little k bounds the size of the parameter, which is basically the solution size. So what you're saying is that the goal is to find a set S of R plus 1 simplices whose cardinality is bounded by K, such that S meets every cycle homologous to zeta. So as I talked about in the example before, of course, if you remove S, the set of simplices S from K, then the class of zeta will be destroyed. All right. So now that the problem has been described, let me very briefly recall some of the elementary notions in parameterized complexity so that I can then state the results. So recall that in parameterized complexity, along with the instance in the question, you have a third bullet, and that's the parameter. And basically, you say that your parameter is bounded by some integer k. So you expect the parameter size to be small. And the tractable algorithms in this context are algorithms that run in fk multiplied by pn time, where f is any computable function of the parameter k, and p is a polynomial function of the instance size n. Now the classes, or the complexity classes in this context, form a hierarchy from W0 through W1 through W2 to WP, and then XP, and so on. And the tractable class is actually FPT, or which is same as W0. And the intractable classes are the ones shown in dark blue, which is W1 through XP. So when you want to show that a problem does not have an FPT algorithm, you basically want to show that the problem is W1 hard or W2 hard or XP hard or so on. And the way to do this is to reduce a known W1 or WP hard problem to the problem at hand. And this reduction has to be an FPT reduction. Okay, so that completes my description of the preliminaries. Let me now state our contributions. So as our first result, we have a polynomial time algorithm for computing the minimum homological hitting set for surfaces. As a second result, we show that the problem is W1 hard, and hence also NP hard for general complexes. So by the way, it's W1 hard with respect to the solution size, which is also called as the natural parameter. To complement the second result, we show that solution size plus degree of the phase poset of the complex. If you take the solution size plus degree of the phase poset as a parameter, then we have an FPT algorithm. So there are many, there are families of complexes that are interesting for which the degree of the phase poset is bounded. And so that in that case, you get a true FPT algorithm in terms of the natural parameter. All right. So now I'll make a few remarks about the contributions. So first, let me say that the polynomial time solution for surfaces largely depends on the structural result for surfaces. And the structural result is that a minimum homological hitting set is always a cocycle. So remember that what we're trying to do is we're trying to destroy cycles. And the optimal solutions actually happen to be duals, which means cocycles. So to complement the structural result, we provided an explicit example of a two-dimensional simplicial complex for which the optimal solutions are not cocycles. And of course, this two complex is actually not a surface. Then we show W1 hardness of homological hitting sets for general complexes. And this is done via an FPT reduction from a known W1 hard problem called the multicolored clique problem. The reduction is fairly complicated and surely it cannot be covered in a talk of this length. So that is all I'll have to say about this result. And finally, we show that, so finally about the FPT algorithm, I'd like to say that the FPT algorithm relies on another structural result, which is that any minimum homological hitting set induces a connected subgraph in the phase poset of the complex. And because of this, we know that the solutions are connected in some sense. So what we actually do is that we just enumerate connected sets in the phase poset, and this brute force enumeration already gives you an FET algorithm with respect to solution size specifically. Okay, so that completes my description of the contributions. I would like to now describe the algorithms to surfaces in more detail because it's the simplest one and hence in many ways the most appealing one. But before we do that, I need to review some of the notions, some more preliminaries, specifically related to cohomology. So here's my brief review. So once again, suppose you're given a simplicial complex K, and then Kp denotes the set of P simplices of K. Then the P cochains are simply the functions going from Kp to Z2. Since we are working with Z2 coefficients, P cochains can be equivalently viewed as subsets of Kp. The P cochain of a complex, the P cochains of the complex K under Z2 addition form a vector space which is called the P cochain group of K, and we denote this by C C superscript P K. And now we define the co-boundary of map. So first, the co-boundary of a simplex, the co-boundary map applied on the simplex is just the set of P+1 cofaces of that simplex. And then if you linearly extend this map from P simplices to P cochains, you get a vector space homomorphism from the P cochain group to the P+1 cochain group. Yeah, so rest of the vector spaces are defined in terms of the kernels and images of these maps. Continuing from last slide, the kernel of the map delta P is called the Pth cocycle group of K, and it's denoted by Z superscript Pk. And the elements of this kernel are called the P cocycles of K. And the images of the map delta P minus 1 the image of the map delta P minus 1 is called the co-boundary group, the Pth co-boundary group of K, and it's denoted by Bpk. And the elements of the co-boundary group are called P co-boundaries. The P cohomology group of K is obtained by taking the quotient of Cpk by Bpk. And now we need, once again, a few more additional definitions, which were kind of dual of what we saw before. So two cocycles are cohomologous if their Z2 difference is a coboundary. The set of cocycles that are cohomologous to a given cocycle Z is called the cohomology class of Z, and it's denoted by square bracket Z. Then a cocycle that is also a coboundary is called a trivial cocycle. A cocycle that is not a coboundary is called a non-trivial cocycle. All right. Now, once again, to build some intuition, let's go through an example. So the set of edges here shown in purple actually form a cocycle. This is because the set of cocycles. Okay, so first let me describe the complex. The complex is a square that is triangulated, so it basically has no holes. And in this complex, you're given the edges in purple is a cocycle because if you observe, the purple edges are incident on every triangle even number of times. It's incident either 0 times or 2 times. So if it's incident, so because of that, it's a cocycle. And also that this cocycle is trivial because it can be written as the co-boundary of the vertices in blue. Okay, that completes my description of the example. I hope this built some intuition for cohomology. Now, one final thing that connects homology and cohomology. And this is a very nice construct. It's called the evaluation map. So let me say what that is. So if you're given a cocycle Z, a P cocycle Z, and a cycle zeta, then you can evaluate Z on zeta. And the evaluation is simply the sum of Z evaluated on every simplex that belongs to the cycle zeta. And because we are doing Z2 additions, the evaluation of cocycle Z on a cycle zeta is either 0 or 1. Moreover, this evaluation map is non-degenerate. This is a very useful property. And what this means is that a cocycle zeta is trivial if and only if it evaluates on every cycle, on every P cycle zeta, it evaluates to 0. And moreover, on the other hand, cycle zeta is trivial if and only if Z of zeta is equal to 0 for all p cocycles C. Okay, so this completes my description of the evaluation map. Now I think all the preliminaries are covered. Oh, there's one more left. It's called the cohomology basis with Z2 coefficients. So let me say what that is. So a set of cocycles Z1 to ZG is called a cohomology basis if the set of classes square bracket Z1 to square bracket ZG form a basis for the first cohomology group of K. Here by G, here I'm denoting the dimension of the first cohomology group by G. So this is what I mean by a cohomology basis. It's a set of cocycles that are non-trivial and are linearly independent. Now the weight of a cocycle is the sum of weights of the edges in that cocycle. The weight of a cohomology basis is the sum of the weight of the basis cocycles. And a minimum cohomology basis is a cohomology basis of minimum weight. Now an important fact about cohomology basis is that they have the set of cohomology bases, the cohomology bases form a metroid structure, and this is something we exploit algorithmically. So now I'm ready to describe the polynomial time algorithm for surfaces. So the algorithm for surfaces goes as follows. So you are given an input cycle zeta. You find a minimum cohomology basis of this input cycle. Then you arrange the cocycles in the basis in the ascending order of weight. And then you pick the smallest cycle, cocycle Z, that evaluates to 1 on this cycle. So here, in the last line, Z1 to ZK minus 1 evaluate to 0 on zeta. And ZK is the first one that evaluates to, ZK is the first cocycle that evaluates to 1 on cycle zeta, and that's it. That's the optimal. That's an optimal homological heating set. So why does this work? So it works because of some nice lemmas, and let me first describe this. So the first nice structural lemma is that a minimum homological heating set is always a non-trivial cocycle, and that's because and this is something that follows from two facts. One is because you're assuming the heating set to be minimal, and it also follows from the non-degeneracy of the evaluation map. The second crucial lemma to prove the correctness is that if you have cocycles Zi from I is equal to 1 to K, then and if all of them are not minimum homological heating sets for zeta, then any linear combinations of these cocycles is also not a minimal heating set. So this is this also follows from the non-degeneracy of the evaluation map. Now the correctness of this algorithm, now we use lemmas 1 and 2, and the correctness follows from the fact that so if Z1 to ZK minus 1 are all evaluating to 0, and ZK is the first one that evaluates to 1, then we know that Z1 to ZK, any linear combination of Z1 to ZK minus 1 also evaluates to 0 and is not an optimal heating set. So and then by the metroid property of cohomology basis, ZK is the minimum weight cycle or minimum weight cocycle that's linearly independent of the preceding cycles, and that's why it's the optimal cocycle or the optimal heating set, because it's a cocycle and the first one that evaluates to 1 on the input cycle zeta. All right, so I hope this gave a flavor of the algorithm and its correctness, and I would finally like to conclude this talk. And for conclusion, I would like to say that although there was some discouraging result about about the complexity for general complexes, which is that it's W1 hard in the natural parameter and it's NP hard and so on. There is still a lot of hope for algorithmic exploration for this construct, because for important classes of complexes like surfaces and manifolds, we have polynomial time algorithm, and also the algorithm is, and also we have an FPT algorithm, the natural parameter, when the degree is small, and there are interesting families of complexes like cubical sets for which the degree is small. So so we have some kind of tractability for interesting classes of complexes for this problem called homological heating sets. And finally, as a final remark, I would like to say that this is not just all theoretical, and we are looking into applications of this construct in establishing robustness or in quantifying robustness of pockets in biomolecules. With that, I'd like to conclude my talk, and I hope this was an enjoyable talk, and thank you for your attention.